In this video, we'll be discovering the double angle formulas and how they relate to the summation formulas we learned previously. So first thing we're going to do is, it seems kind of silly, but we're going to review and see how we can double something without multiplying it. If I ask somebody to tell me what double 2 is, they will tell me that the answer is 4. And when I ask them how they got that, they'll say, oh, I just did 2 times 2. And if I ask them to do the same thing, find double 6, then they'll tell me that the answer is 12. Because they'll say, oh, well, Mr. Raymond, double 2 and double 6 just means you multiply it by 2. But there is a way to double something without multiplying it. So yes, you can double 6 by multiplying it by 2. But another way to double something is to add it to itself. So I could also write 6 plus 6, and that will double 6. If I wanted double 2, then I know that the answer is 4, and I can do that by doing 2 plus 2. Well, what if I wanted to double something that wasn't necessarily a number that you know? What if I wanted to double an unknown value? So for example, double A. Well, double A is 2A. But what's another way of solving that? By doing A plus A. And this is the idea that we're going to exploit so that we can find our double angle formulas. So the first thing we're going to do is look at some of our summation formulas and see if we can turn those into double angle formulas. So here's the summation formula for sine. And what we did in previous practice is we said, oh, well, let's just say that A is equal to, I'm just going to make these numbers up, 30 degrees and B is 45 degrees. And we were allowed to do that because these A's and B's, they're unknowns. We don't know what they are. We decided to call them 30 degrees and 45 degrees. So let's make another assumption. Let's say that sine of A plus B, well, let's say that A equals B. So now it's the sine of A plus A, which from the previous slide, sine of A plus A is the sine of double A. So now you might be able to get an idea of what we're doing here, but we just created an expression for the sine of 2A, double some angle. So now let's put an equal sign and figure out an equation for it. So if we change all of the B's to A's, the formula becomes the sine of A times the cosine of B plus the cosine of A. Oop, excuse me, I just said that we're changing all all B's to A's. So that should be cosine of A plus cosine of A times the sine of A. All we've done is changed all of the B's to A's because we've made this expression or this equation here. We have stated that A equals B. Well, we can rearrange these. This is multiplication. So the commutative property of multiplication says I can switch these two around. I can instead write it as cosine of A times the sine of A plus cosine of A times the sine of A. And if you notice, these two are the exact same thing. Well, again, if you're adding the exact same thing, you're doubling it. We actually have another double off on the right-hand side too. It's now 2 times the cosine of A times the sine of A. This is our first double angle formula. This is one of those double angle formulas that will be very helpful in the future. So here's our first one for the sine. We're actually going to skip over cosine for a minute and jump to tangent. We'll come back to cosine later. So let's go ahead and do the tangent double angle formula. Now I'm actually willing to bet that there are quite a few students out there that can figure out the double angle formula for tangent without me going through it. So I encourage you to try and find a moment and pause this video and see if you can figure it out without me. But I'm going to go ahead and start it now. I'm going to start by stating that A equals B. This way now we can replace all of our B's with A's, which gives us a double angle on the left-hand side here. And then on the right-hand side, we have the tangent of A plus the tangent of, instead of writing B, I write A, 1 minus the tangent of A times the tangent of A again. Now, if you'll notice, again, we have something plus something, which means in the numerator, we're going to have 2 tangent of A. Down here, we have 1 minus, well, tangent of A times tangent of A. Well, if you multiply something by itself, it becomes squared. So this is tangent squared A. Off on the left-hand side, A plus A. Again, that is doubling something. So here we have another double angle formula. This is another one of those double angle formulas that will help us out quite a bit in the future. This is the one for tangent. I did save cosine for last because cosine's a little bit weird. We'll discover that there's actually 3 of them for cosine. And it doesn't matter which one you use, but I'm going to go ahead and show you guys how to figure out each one. So we're going to start the double angle formula for cosine the same way we did with tangent and sine. And this is actually no different. This will give us the first double angle formula. So if you want to, you're welcome to pause this video and see if you can figure it out before me. So I'm going to again start by saying that A equals B. This now allows me to write down an A instead of all of my B's. So cosine of A plus cosine of A equals cosine of A, excuse me, I said cosine of A plus A is what I meant right here, times cosine of A minus sine of A times the sine of A. So here's where we get to do a little bit of thinking and say, wait a second, just like we did with tangent, we're multiplying cosine of A times cosine of A. Well, that gives us the squared. So cosine squared A minus, we have the same thing here, sine of A times sine of A. So it gives us sine squared A. Off on the left-hand side here, we've got A plus A, which is double A. And we're taking the cosine of it. So this one really isn't any different from the sine and the tangent, but we're going to do something with this to make it a little bit different. So here is our first double angle formula for cosine. This is one of 3 double angle formulas for cosine. Let's see where the other 2 come from. Now, a student who's thinking back to things that we've just done previously might look at this and say, wait a second, this looks like a Pythagorean theorem, or a Pythagorean identity. And you're right, it looks very, very similar to one, but it is not exactly equal to one. So as a reminder, Pythagorean identity says that sine squared theta plus cosine squared theta equals 1. This is your Pythagorean identity, and as hard as you try, it will be impossible for you to rearrange it to get cosine squared theta, or A, it's just a variable, minus sine squared variable. It is impossible to rearrange Pythagorean identity such that it looks like this. But we can use Pythagorean identity. If you've done enough of those simplifying trig function problems, then you'll remember that you can rearrange Pythagorean identity. We can rearrange it such that sine squared theta is equal to 1 minus cosine squared theta, and we can rearrange it so that cosine squared theta equals 1 minus sine squared theta, and you get those by subtracting either sine squared theta or cosine squared theta. This is the key to how we're going to find our alternate versions of these 2 double angle formulas. So let's go ahead and see how we can mess around with these. I'm going to start here on this left-hand side by noticing cosine squared theta. Well, I can rewrite that as cosine squared A. Theta is just a variable. So I can rewrite cosine squared A as 1 minus sine squared A. These are equivalent statements because of that Pythagorean identity. So minus sine squared A, and all of this still equals the cosine of 2A. Well, now we've just got to do a little bit of simplifying. 1 minus sine squared A minus sine squared A, well, that's 2 negative sine squared A's. So cosine of 2A, or double angle, is 1 minus 2 sine squared a. This is our second double angle formula for cosine. Well, now let's do the exact same thing with sine squared instead of the cosine squared function. This one is a little bit different because you've got to be careful with your negatives. So first I'm going to say, well, sine squared a, sine squared theta, I can replace it with an equivalent statement. Now I'm going to write this and be very particular in the way that I'm writing it. So cosine of 2a is equal to cosine squared a minus. Now here's where students make mistakes. Sine squared a needs to be replaced with 1 minus cosine squared a. I cannot leave these parentheses off. It is very, very, very important because we are replacing sine squared a, but we're also subtracting sine squared a. So I need to make sure that I'm careful about my parentheses. If you don't use parentheses, you're actually going to end up with equaling 1, which we should know is incorrect. Excuse me, you're going to end up equaling -1, which we should know is incorrect. But just in case, make sure that you put those parentheses around it. So when we put those parentheses around it, it means that we need to distribute that -1. So cosine squared a minus 1, and here's where those parentheses are required, plus cosine squared a. So now with the commutative property of addition, I can add those two functions together. Cosine of 2a equals double cosine squared a minus 1. This is our third and final form of the double angle formula for cosine. So there you have it. There are all of our double angle formulas for sine, cosine, and tangent. In the next slide, we're going to use it once, but really it's the same thing as the summation formulas use. Same thing. That's it. Let's go ahead and practice it. So here's our first example. If the sine of theta equals 4/5 and theta is in quadrant 1, find the cosine of 2 theta. So this looks very similar to our sum and difference problems. The only difference is what it's asking us to find. We need to find the cosine of 2 theta. Well, that's double theta, which tells me I need to look at my double angle formulas. Specifically, I'm going to look at the cosine double angle formulas. So I'm going to go ahead and pop those on the screen, and we're going to take a look at those. So here are our double angle formulas for cosine. Now, I'm going to use these double angle formulas, and it turns out it doesn't matter which one I use. Now, most students are going to be more comfortable using this first one just because it means that they can use the same one over and over and over. And that's fine. It does mean you're going to end up doing a little bit more work than you probably need to sometimes. So I'm going to go ahead and use this first one, and then I'll do it again using the easier one, and I'll tell you guys why I know it's easier. So to start off with, in order to solve this problem, I need to know what the cosine of A is. Well, in this case, theta. I need to know what the cosine of theta is, and I need to know what the sine of theta is. Well, luckily, they give me the sine of theta. They tell me that sine of theta, let me change colors. The sine of theta is 4/5. So when I'm trying to find the cosine of 2 theta, I can go ahead and write something squared minus 4/5 squared. So now I just need to figure out what the cosine of theta is. Well, luckily we've done a bunch of these problems from the summation. So if we're in quadrant 1, then I've got a hypotenuse of 5, an opposite of 4. I just need to use Pythagorean theorem to figure out what the adjacent is. Well, this is a Pythagorean triplet, so it's 3. So here's my opposite, here's my adjacent, and here's my hypotenuse. So I end up with a cosine of adjacent over hypotenuse, 3/5. Now it's just a matter of solving the problem. Cosine of 2 theta is equal to, when you're squaring something, that's multiplying it by itself. So 9/25 minus, well, 4/5 squared. is going to be 16 over 25. Now we've got to subtract these fractions. Luckily, they already have the same denominator. So cosine of 2 theta is going to be just straight 9 minus 16, go across the top there, negative 7, and then we keep the denominator. This is our solution for the cosine of 2 theta. Now, it's not that bad, but we can actually make it a little bit easier. I told you that there is an easier form or easier version to use. The reason this one is a little bit easier is because we already have the information. If we use this second formula, we don't have to worry about finding the cosine. So let's see what happens if I decided to use the second formula instead. Cosine of 2 theta is equal to 1 minus 2 times, well, sine of theta is given in the problem, 4 over 5 squared. Cosine of 2 theta equals 1 minus 2 times, well, that's 16 over 25. Cosine of 2 theta equals 1 minus 16 times 2 is 32 over 25. Well, now we've just got to subtract a fraction and a whole number. Cosine of 2 theta is equal to 25 over 25 minus 32 over 25. Well, 25 minus 32 is also negative 7. Keep those denominators. In both cases, we've discovered that the cosine of 2 theta is negative 7 over 25. The one in white requires me to do a little bit more pre-calculus stuff, but it's still just right triangles. The one in red requires me to do less pre-calculus stuff, still right triangles, but more old arithmetic. So when I say easier, I guess I more so mean that there's less of the pre-calculus knowledge and more of the previous knowledge. So if you're a little bit weaker in that arithmetic, I would definitely practice using that arithmetic in a low-stakes environment like a homework or a practice.